Section 5.1 from Unit 4, Systems of Linear Equations and Two Variables. Most of this should be a review from information in a 1010 or a Math 990 course. Our learning target today, solve a system of linear equations in two variables, and then we'll look at an application of that process. Now, just some important background information. Equations, you've been solving equations for a long time in your algebra courses. Typically, equations have one variable to solve for. So for example, this equation here, a plus 3 is equal to 7. If you have one equation with one variable, it's very easy to solve, or in most cases, I should say, it's very easy to solve and isolate that single variable. In this case, obviously, you would subtract 3, and you have one unique solution for this equation, a equals 4. That is the only solution for this equation. Now, this one here, we have one equation, but now we have two unknowns, a and b. And the problem here is, and I guess it's not really a problem, the issue is we can still solve this equation. However, it does not have one unique solution. What I mean by that is, let's keep track of it here in the form of a table. We could have a is equal to 1, b is equal to 6. There's one possible solution. Or a could be 2, b could be 5, or a could be 3, b could be 4, or a could be 4 and b could be 3, a could be 0, b could be 7. The point I'm trying to make is this list can go on and on and on. Matter of fact, it can go on to infinity. There's an infinite number of possible combinations of values that will work if we consider also the negative values, like a could be -1 and b could be +8. And so if we have one equation with two variables, there's an infinite number of solutions to that equation. And rather than trying to consider all of the solutions in tabular form, the more common way of representing solutions to an equation that has two variables is actually by graphing. And I wish more instructors and more students had an emphasis or a deeper understanding of what a graph actually is. If we were to graph this equation, a plus b equals 7, and let's say that the horizontal axis is our a axis and the vertical axis is our b axis. If we graphed all of these points on this coordinate system, let's see what it would look like. So 1, 6, or we have 2, 5, or we have 3, 4, or 4, 3, all the way over here to 0, 7. All of these line up in a perfect line. This is a linear function. A plus b equals 7 is a linear equation. That's actually what we're doing when we're graphing any equation or function. We're actually graphing or we're producing a collection of points that represents solutions to an equation. All of these points and any point on this line represent possible solutions to this equation, a plus b equals 7. So that's actually what a graph is showing, or a visual representation of solutions to an equation in two variables. But it still doesn't change the fact that this one equation has infinitely many solutions, whereas this equation here, when it only had the one variable, had one unique solution. So if we did want to find unique values, a and b, what we need is to add one more condition. So right now the condition is when you add two values together, the sum is 7. A plus B is equal to 7. If we added one more condition to that statement, saying if you add two numbers together, the sum is 7, but if you subtract those same two values, the difference is -3. What we have created now is what's known as a system of equations. We have the first condition, a plus b is equal to 7, but now we have a second condition, a minus b is equal to -3. Now if we considered all of the possible solutions for this second equation, a minus b equals -3, we need to have values that subtract to get -3. For example, if a is 4 and b is 7, those subtract to -3. Or if a is 3 and b is 6, then the difference there would be -3. We could also have a equals 2 and b could be 5. And again, this list can go on and on and on. We could have a equals 0 and b could be 3. So if we graphed this, or if we wanted to represent this tabular form of solutions, and again, this list could go on and on and on and on, but rather than making an infinitely long list of values in a table, it's a little more concise to represent this data on a graph here. So now if we graphed this graph, let's get a different color here. Okay, so 0, a is 0, b is 3, or a is 2, and b is 5, or a is 3 and b is 6. What ends up happening is those solutions line up on this line. And what we're looking at with this graphic right here, where we have the linear line here in black and the one in blue, this is a representation of this system of equations right here. It's called a system of equations when we have two equations containing the same two variables, and we're solving this system of equations simultaneously. So we need to figure out a solution that satisfies both this equation and satisfies this equation. So again, just this top equation alone, a plus b equals 7, had an infinite number of solutions on this black line. And then this equation, a minus b equals -3, has an infinite number of solutions on this blue line. However, if we consider solutions that satisfy both equations at the same time, there's actually only one point now that we can identify that satisfies that condition, and it needs to be a point that is contained on both lines. So we need to find a point that's contained on this black line and on the blue one, and it's this line, or it's this point right here, 2, 5. When a equals 2, and when b equals 5, and again, we identify that point based on the fact that it's a point on both lines, the blue line and the black line, which means it's a solution for both equations. And that is the graphical way of thinking about a solution to a system of linear equations. And like I said, hopefully most of this is a review discussion. It's things you've discussed before. But again, the point I'm trying to make here is when you have one equation with two variables, that's going to have an infinite number of solutions. If you add another equation that has the same two variables, you create a system of equations, and then you can find one unique solution that satisfies both equations. And graphically speaking, it's the intersection of those two linear functions, or those two linear equations. In this case, the solution would be a equals 2, b equals 5. Now, a few other things to consider. We have looked at a case kind of like this one where we had a system of equations that contained two linear equations and it had one unique solution because the lines intersected. And you can see I've got some example linear functions here, y equals x plus 2, y equals negative x plus 4. Those intersect one point, so that has one solution. This other picture I've drawn here, it is still a system of equations. 2x minus 2y equals 2, and then negative x plus y equals negative 1. They're two separate equations, but in actuality, when you graph both of these, they end up being the same line, which really means that these are the exact same equations. This top one has just been multiplied by negative 2. So there really are two lines graphed here. It's just one is on top of the other. In these two situations, there are solutions to these system of equations. In this case here, there's one unique solution because the lines intersected once. In this case, there are infinitely many solutions because both lines intersect with each other an infinite number of times. So both of these system of equations has a solution. This is one unique solution. This is infinitely many solution. If that's the case, our textbook uses a term called consistent. When a system of equations has solutions, it's called consistent. So these are consistent systems of equations. And then that breaks down further into an independent and a dependent. And they're both considered consistent because they have solutions. An independent system of equations has one unique solution. A dependent system of equations has infinitely many solutions. Now over here, this system of equations, y equals 2x plus 3 and y equals 2x minus 4, you notice that the lines are parallel because they have the same slope, slope of 2. So there are no points of intersection between these two lines, which means there are no solutions. That's what's called an inconsistent system of equations. So again, just to review, if the system of equations has solutions, whether that is one unique solution, independent, or infinitely many solutions, dependent, that's called a consistent system of equations. If the system of equations has no solution because the lines are parallel, that's called an inconsistent system of equations. Okay, so that's just some background information before we actually get into our learning targets. Our learning targets for today were to solve a system of linear equations in two variables. And it's going to use the two methods which I'm sure you're familiar with called the substitution method and elimination method. So we'll start with substitution method first, and we're going to solve a system of equations that has one solution. It's called independent. And we're going to solve using the method substitution. So you can see we have this top equation, 3x plus 4y equals 14. So this one equation has two variables, so we can't solve for a unique solution unless we add one more condition here with the second equation that contains the same two variables, x and y. Now, the value for y is given here. It's negative 2x plus 1. If this y variable has this value, then this y variable also has the exact same value because it's the same variable. So what we do is make a substitution. This expression here, negative 2x plus 1, gets substituted in to the top equation for y, and so that top equation can be rewritten as 3x plus 4. Instead of y, you make the substitution of negative 2x plus 1. That equals 14, and it may look, at least by appearances, that we've just made things more complicated. In actuality, we haven't. Originally, this top equation had two variables, and you can't solve one equation if it has two variables. This equation now, after we've made the substitution, only has one variable, the variable x. And we can solve an equation if it just has one variable. Just solve by combining like terms. We get rid of parentheses by distributing the 4, and then subtracting this 4 over to here gets us 10. So dividing by negative 5 means that x equals negative 2. Now, one common mistake students will often make is thinking, okay, I've solved something, so I must be done, but we've only solved for one of the variables. Remember, we're solving for x and y. Right now, I just have a solution for x. So we need to go back and substitute now to find the value of y. And we have the value of y here as negative 2x plus 1. And now that we have the value of x, we can substitute that in there and say that y equals negative 2 times our value of x, which is negative 2 plus 1. Negative 2 times negative 2 is 4. 4 plus 1 equals 5. So we have x equals negative 2, y equals 5. It is correct now to represent your solution as an ordered pair, negative 2 comma 5, because remember what we're actually doing is finding on a graph the intersection point between this line and this line. If we were to graph both lines, they would intersect at this point, negative 2 comma 5. So it is correct to represent your solution in this case as an ordered pair, negative 2 comma 5. So that's the substitution method. I would recommend substitution method when you have an equation in this form. It's called standard form, where both variables are on the same side of the equation. This one obviously is slope-intercept form, y equals mx plus b. When you have a system of equations where one of the equations is in standard form and the other is in slope-intercept form, then substitution works really, really well. Okay, now the other method rather, elimination method. This one I'd recommend using when you have both equations in standard form. You see how the variable x and y are on the same side of the equation in both of these equations. So substitution method still can work. You would have to rearrange one of these equations and get and isolate one of the variables. But if they're already lined up where the variables are lined up and the constants are lined up, this elimination method tends to be a little bit quicker. And the reason it's called elimination method is what we want to do is try to add the two equations together and eliminate one of the variables. Now that can only be done if we have variables that have opposite coefficients. So for example, I've got negative 8 as a coefficient of y. If I had positive 8 as a coefficient of y here, then those would be opposite coefficients. And when I tried to add the equations together, then the y variable would eliminate because you have opposite coefficients. So what you can do is multiply an entire equation. As long as you multiply everything in the equation by the same value, you're not changing the solutions to the equation, you're just changing the appearance. So for example, if we multiply the entire top equation by 4, that top equation becomes 12x plus 8y equals 56. And then we have not done anything to the bottom equation, so that stays 4x minus 8y equals 8. So what we have done is created a situation where we have opposite coefficients for one of the variables. Now, if we added these equations together, the y variable eliminates because we have 0y, which is 0. And then that leaves us with 16x equals 64. If you divide by 16, we get x equals 4. Now what we need to do is go solve for y. So we choose any one of the original equations here. I'm going to choose this top equation. So that top equation is 3 times x, which we now know is 4. So 3 times 4 plus 2 times y equals 14. And then 3 times 4 is 12, so 12 plus 2y equals 14. Subtract 12 and we have 2y equals 2. Divide by 2 and we get y equals 1. So then our solution would be the ordered pair 4, comma 1. Now, an example of infinitely many solutions or a dependent system of equations. We notice here that the variables are lined up. They're both in standard form, so I would choose in this case to use the elimination method. And trying to get opposite coefficients between x, for example, here, 4x and 3x, the least common multiple of 3 and 4 is 12. So I'd want to get 12 as my coefficient for the x values. So if I multiply the top equation by 4 and the bottom equation by -3, and the reason I'd want -3, remember, is you want opposite coefficients, one positive, one negative. So now that top equation becomes 12x minus 24y equals 48. Bottom equation becomes negative 12x plus 24y equals negative 48. And this is the unique the unique situation that you look out for. Everything eliminates, and we have the statement of 0 equals 0. Whenever you have this statement 0 equals 0, that's an indication of a dependent system of equations, and you would write infinitely many solutions. So if you remember, what that means is both of these equations are they're actually the same equation. They're the exact same equation. You can see that here. And what that means is if we graph both of these equations, what we're graphing is the exact same line, on one on top of itself. Matter of fact, if we took, for example, this top equation right here, 3x minus 6y equals 12. If we rearrange this equation, now that it's in standard form, we could rearrange it into slope-intercept form. So if I subtract 3x and then divide by -6, what I'm trying to do is get this into slope-intercept form. What we would have is y equals 1/2 x minus 2. So this is the slope-intercept form of both of these equations. So looking at the graph, let's see, we have a y-intercept of -2. The slope is up 1/2. So the graph for both of our original equations looks like this. So you'd graph one on top of the other. That's why there are infinitely many solutions. Now there's a little point of confusion sometimes with students where they confuse infinitely many solutions with all real numbers. And it's not the same thing. All real numbers and infinitely many solutions are two completely different ideas in the context of what we're talking about here. Remember, solutions to a system of equations are points on a graph. So there are an infinite number of points on this line that represent solutions to this system of equations here. But that's not the same as saying all real numbers are solutions. You can't just choose any random x and y values and have that be solutions to this system of equations. They have to be x and y points that lie on this line right here. And there are an infinite number of them. So one of the questions that sometimes comes up is, well, if there are infinitely many solutions, then what's one of the solutions? Or tell me a few of them. What's an x and y combination that would satisfy each of these equations? Now you can see that it has to be points on this line right here. And so you can see, for example, the point 0, 2 is one of our points. That's our y-intercept. Or 0, -2 rather. This point right here is the point 2, -1. So both of these would actually be solutions to this system of equations, and we could identify any point along this line. So what the book is going to ask on the homework, and this would also be a requirement on the exam, if there are infinitely many solutions, you must still represent your solution as an ordered pair. What I mean by that is what you circle as an answer is not only this statement, if there's infinitely many solutions, but also an ordered pair statement. And because there's not one unique solution, you're not going to have an ordered pair statement like this one, 4, 1. Your ordered pair statement is going to look a little bit different if there's infinitely many solutions. And here's what it's going to look like. So any solution to a system of equations is in the form of an ordered pair x comma y. And textbooks do this a little bit differently depending on which college algebra course you're taking. Our particular textbook, and this is the convention I'm going to follow because it's the textbook we're using, says to let x equal t. T is just a parameter. T can be any real number. So we're going to let x equal t. And then we solve for y, which we already did right here. Y is equal to 1/2 x minus 2. Y is equal to 1/2 t now minus 2, because remember we're letting x equal t, so I just replace the x with a t. So then our solution, instead of x comma y, we replace the x with a t, and it becomes t. And then instead of the y here, we replace that with this, 1/2 t minus 2. And this is the solution to the system of equation in terms of the parameter t. And what we can do with this now is use this statement to produce any point on this line, which would be a potential solution for the system of equations. And the way that you do that is you let t be any real number. For example, if t is equal to 0, then you have 0 comma 1/2 times 0 here would be 0. 0 minus 2 is -2, so it would be 0 comma -2, which was this solution here. If we let t equal 2, so this t is 2 and that t is also 2, then we get the solution 2 comma, let's see, 1/2 of 2 is 1, 1 minus 2 is -1, so then that gives us 2 comma -1, which was that solution right there. So this solution statement, t comma 1/2 t minus 2, will produce any point on that line, which again is a solution to the system of equations, and there's infinitely many of them. So what I'm trying to say, bottom line, is what you would circle on an exam or your homework would be two things. First, you recognize that 0 equals 0 means that you have infinitely many solutions. So you need to have that statement there. Then you need to go through and write the statement as an ordered pair, in this case t comma 1/2 t minus 2. So another example of a system of equations, this one's going to have no solution or inconsistent. What that means is these are two lines that have the same slope but different y-intercepts. So they're parallel lines which never intersect, so they're not going to have any points in common, hence no solution. What you would see is this. In the process of trying to solve this, for example, if I wanted y to eliminate, if I wanted to get opposite coefficients for y, I'd want to have a -6 here and a +6 here. So what I would do is multiply the top equation by 3, bottom equation by 2, and what we would have is 24x minus 6y equals 15. -24x plus 6y equals 14. So the variables eliminate. So on the left side we have 0, but on the right side we have 29, and 0 does not equal 29. This is an untrue statement. If you remember from the problem above, if you have a true statement like 0 equals 0 but no variables, that is an indication of infinitely many solutions. When there are no more variables and you have an untrue statement like 0 equals 29, that's an indication of no solution. And that's actually all you need to write on a problem like this. So that takes care of our first learning target, and hopefully this was just a really good review from things and techniques that you have learned in previous algebra courses. Our last learning target is just looking at an application. This is one of several types of application problems in the homework 5.1. This one's called a mixture problem. There are others that are distance equals rate times time problems, like a boat traveling in a river current or airplanes traveling against the air and with the air. So you'll see all sorts of applications. We'll just do one example here of what's called a mixture problem. So we have this biologist with brine solutions, and one of them's 5%, another one's 20%, but whatever this biologist is doing, it requires a mixture that's only 14% salt. And so what this biologist is going to need to do is mix the 5% mixture with the 20% mixture in order to end up with a 14% mixture. So the question is, how much of each mixture should be mixed in order to have 1 liter of 14% salt? One of the first things you do when you're doing any application problem, especially if there is no function or equation or anything like that given, is identify your variables. And since we have two different types of mixtures, I'm going to choose to have two different variables. So let x equal number of milliliters of the 5% salt solution. And you want to be as descriptive as you can when you're assigning variables. What I mean is you're not just going to say x equals 5% salt solution. You want to say it's the number of milliliters or the amount. And then y, I'm going to say, is the number of milliliters of the 20% salt solution. Now you got to be careful here. You don't want to have too many variables, because in order to solve for variables, remember, you have to have the same number of equations as variables. So if I have two variables, x and y, in order to solve for that, I have to have two equations now. Like this, I'm going to have to form a system of equations because I have two variables. So one of the equations we're going to form is going to come from this statement right here. We need to obtain a mixture that's 1 liter in amount. So if I add this solution to this solution, it's going to end up being 1 liter. So x plus y is going to equal, and I'm going to call it 1,000. The reason being, I've defined x and y in terms of milliliters. So however many milliliters of x, I'm going to add to however many milliliters of y, and that's supposed to equal 1 liter, which is 1,000 milliliters. So x plus y equals 1,000. Now the next equation can come from this statement that it needs to be 14% salt. So what needs to happen now is my first solution, x, contains 5% salt, and there's x number of milliliters of that. So 0.05 is the 5% salt, and it's 5% of x, which is the number of milliliters. I'm going to add that to 0.2 because there's 20% salt in the y mixture, and I'm adding y milliliters of it. And notice what I have. I have a percentage of an amount of milliliters, so it's 5% of x milliliters plus 20% of y milliliters. And it's supposed to equal 14% of the 1,000 milliliters. And this is important. It's actually a mistake that students quite often make. When you're talking about mixtures and percentages of mixtures, you have to have a percent of a fluid amount. So it's 5% of this many milliliters plus 20% salt of this many milliliters has to equal 14% of this many milliliters. You can't forget that it has to be a concentration multiplied by an amount of milliliters. And to simplify this here, I'm going to go through a few steps to simplify this a little bit. X plus y equals 1,000, and we have 0.05x plus 0.2y equals 140. And I'm actually going to take and multiply this equation by 100 again, because that's going to move the decimal spot 2 to the right. So then what I would get is x plus y equals 1,000, and then 5x plus 20y equals 14,000. Okay, so I just did some basic simplification to get rid of the decimals. Now I can look at elimination. If I wanted to eliminate the x variable, for example, I could multiply that top equation by -5. And then now I have x variable has eliminated, leaving 15y equals 9,000. And 9,000 divided by 15 is 600. And remember what y is. Y is the number of milliliters of the 20% solution. So according to this, what we need is 600 milliliters of the 20% solution. And we already knew that we needed 1,000 milliliters total. And if 600 of that is the 20% solution, then we know that we're going to need 400 milliliters of the 5% solution. And that's the mixture we're going to need to create our 14% mixture. We need 600 milliliters of the 20% solution, 400 milliliters of the 5% solution. What that's going to give us is 1 liter or 1,000 milliliters of a 14% concentrated brine solution. So that is just one example of the types of applications for systems of equations. And really what it boils down to is the number of variables you assign is going to be equal to the number of equations you have to have. So if you assign 2 variables, you need 2 equations. If you have 3 variables, you need 3 equations, which we'll talk about in section 5.2, systems of equations with 3 variables. So anyway, we have an inconsistent system, no solution. We have a dependent system with infinitely many solutions, and we talked about how to represent that solution as an ordered pair in terms of a parameter t. And then here we had just a brief refresher on using the elimination method to solve a system of equations, or the substitution method to solve a system of equations.